Or,
Great.
all right. Take it away.
All right, perfect. Thank you very much, the organizers, for giving me this time today. My name is Logan Murphy. I'm in the software engineering and modeling group at the University of Toronto. And this talk is based on a project I'm working on with Marcia Chechik, Torin Vigor, Alessio Di Sandro, and Rami Shaheen about leveraging Lean for safety modeling. So a quick outline of the talk. I'll do a quick introduction to the domain that we're hoping to use Lean in and what we hope to get out of it. I'll talk about the previous work that motivated this project. One thread is the Minta toolbox that we've been developing for a few years for model management in assurance cases in software. The other is looking at formal argument structures in assurance cases. I'll talk a bit about what our approach has been for integrating Lean with the Minta tool. I'll give an example of the workflow for that integration, and then we'll talk a bit about the contributions we've made and some of the lessons we've learned, and then talk about where we go from here. So this is all based on the problem of safety in software. So just like in traditional fields of engineering, you don't let someone build a bridge unless you do the proper inspections and codes and testing or whatnot. And that's increasingly the case for software engineering, especially in safety critical domains like aerospace or automotive. So basically, we want to know that the software we deploy is safe and won't, exhibit undesired behavior. And this has been a problem for decades, and we've developed all sorts of different ways we can mitigate this. So testing and benchmarks, code review, more formal tools like model checking and theorem provers or and it's, again, important for safety critical domains. So the main one for us is automotive. So cars are being increasingly developed and shipped with lots of complex software that's always interacting. So this is a very important point for engineers and for regulators. But if there's so much different sources of evidence or persuasion that software is correct, the question is, how do you manage all that evidence? So one thing that some industries have embraced is these goal-based safety cases. So the deliverable here is an argument, a structured argument that the system is safe to operate in its intended context. And the author, who is usually like a safety engineer, can determine what sort of evidence is appropriate. And then we can generalize beyond safety cases because sometimes you don't only want to know about safety requirements, but security requirements and privacy requirements. And so this is sort of what a traditional safety case or assurance case looks like. It's a series of claims about the software system or any sort of system. And you support that claim by documenting different kinds of evidence, context, and what assumptions you have. And so you can see on the right here, you have these sort of top level claims, and these are being incrementally decomposed into smaller, simpler claims, and you can have different context and evidence to support those claims. But of course, this sort of format for an assurance case is not very manageable, especially at scale and over time. And so people have developed these more formal notations, this sort of tree-like structure where at the root you have your top level claim, your core claim, and then you're incrementally dividing that into smaller claims and using different annotations for context and justifications. And at the very bottom, you have your evidence or your assumptions. So this is a proof assistant workshop we're in, and so it's worth pointing out the difference between an assurance case and a proof, right? So an assurance case is clearly not a formal proof, and it shouldn't be. It has to be reviewed by stakeholders, engineers, and regulators, and it's not even really an informal proof, right? Even an formal proof should be based on deductive reasoning. You have your axioms, you have your inference rules, and then it's a tight logical argument. But assurance cases are always primarily built about inductive reasoning, right? You have this array of evidence that suggests a certain level of confidence that errors are sufficiently unlikely. And so for this reason, the full formalization and automation of assurance cases is not really realistic or desirable. But there is still, because they're essentially structured arguments, and any kind of argument has some sort of implicit deductive reasoning. So there is actually deductive reasoning in these assurance cases, and because humans are notoriously bad at using deductive reasoning, especially when it's left implicit, there's fallacious reasoning. So sometimes an assurance case is created and it looks like a sound argument, but it's actually missing some assumptions, or things are too implicit, and then it's not reliable for the safety mitigation process. And this has been studied in literature several times in the last decade or so. So one of the primary goals of our research is to identify the fragments of assurance cases where strict deductive reasoning can be made explicit, and then use a formal or deductive framework to validate those fragments. And of course, this is where lean comes in. We really want to use lean as a framework to express and prove properties of these assurance case claims, and also to use lean as a tool to generate formal evidence that can be used in these claims. So like I said, this current work builds on two threads of previous work. So the first one I'll talk about quickly is just this suite or toolbox of different model management tools that we've been developing for the last few years. And more recently, we've been making them more suitable for realistic assurance case management in model-driven engineering contexts. And if you want to see more information, you should check out the GitHub link here. More interesting for this audience is the formality of the assurance case claims. So one framework that we proposed last year is based on this fragment of an assurance case where you have a top-level claim, this C1 here, and you're using a strategy to decompose it into these smaller claims. So you might have, this top-level claim that's sort of too large or too broad to have like one piece of evidence that can support it directly. And so you need to split it up. Like if this system that the top claim is about has 3 component systems, you might want to generate evidence for each of the component systems. And then, through this argument over subsystems, you can then support the top level claim. So this is the fragment of assurance cases that we're looking to validate. So in the framework we published last year, we saw that if we restrict ourselves to claims of a particular form, basically you have a type, you have a set of elements of that type and a predicate or property on that type. And then the claim is just basically is assigned the logical sentence that for every element of that set, the predicate holds. So it's pretty simple from a formal perspective. Now, given a claim, a strategy, like I said, is basically just a map associating that target claim to a list of subclaims, right? And so we call that strategy deductive if the iterated conjunction of all those subclaims imply the parent claim. And so in this framework, we provided or identified at least two useful classes of decomposition strategies, domain decomposition and property decomposition. As the name suggests, domain decomposition takes the set of elements you're reasoning about and splits that up into subsets. And property decomposition uses these auxiliary properties that when you take their conjunction imply the parent property. So this is an example of sort of the goal we got from that paper last year, right? So you have this is a property decomposition strategy. Your parent claim is that a property holds for every element of a set. The strategy is a property decomposition. You have this relatively simple, set theoretic justification that, you can actually decompose this claim into these subclaims. And then the context for why this justification matters is that one of the proofs in that paper proved that this is a sufficient condition or sufficient justification for this decomposition to be deductive, right? But this is still not quite as tight or as sufficient from an evidence perspective as we could get, because what we have here is a formal condition, right? And so rather than saying, okay, we have this template for a sufficient property and we're pretty sure that this actually, fits in that template, it'd be better if we could have a concrete proof, right? So we have this sort of formal decomposition strategy, and the justification is just that we can have a formal proof that this set theoretic statement holds, and then instead of using just the context from our pen and paper proof, we have some evidence that's actually a formal proof in lean that we can use as evidence. Obviously, lean is not necessarily perfect. There's always possible for bugs, but passing something through the lean kernel is still much better than implicit deductive reasoning or even just a hand waving a pen and paper proof. So this is something we would really like to get to use in our real assurance cases. So as we expected, it was pretty easy to formalize the justification frameworks. It's just elementary set theory. These are just the type signatures of the two main theorems from that paper. Here, gamma is just a data structure representing what's the defining characteristics of a particular strategy. And then if you want to show that the strategy is deductive, you can show that it's justified as per that, justification definition I just showed. This top one's for property decomposition and this one's for domain decomposition, but it's not necessarily important. So now that we have this formalization, we want to see if we can use this in our model management toolbox to actually help software and safety engineers in their assurance case management and verification. So to begin this integration process, we needed to experiment with some different sort of system models, because when you're making a claim about a system, you need a system to reason about. So we just started with labeled transition systems. It's just these, directed graphs, a set of states, a set of transitions, or a set of states, set of actions, and a set of transitions. And these are, ubiquitous in sort of more formal software engineering. So of course we can define those easily in Lean, and then we developed a framework to make claims about the paths of an LTS using temporal logic properties easily enough. But importantly, because our end goal is to leverage Lean in this software modeling tool, and we don't necessarily want to restrict our users to only ones that can write Lean themselves. And so the question is, how do we express a claim decomposition strategy about a system in a way that a user can input, but that Lean can also understand? So this is sort of the scheme that we're working with at this point, right? So we have our formalism or a class of models like transition systems. Those are formalized and associated with a Lean type that we've written. That formalism is instantiated by a particular system model in Minta, which is then translated directly to a Lean model using a model-to-model translation that we've written. The user has an informal strategy whose subject is that Minta model. And somehow we need to take this informal strategy and turn it to a formal strategy, which is a Lean expression, whose form is completely determined by the particular Lean model that we've written, or that we've translated the system model to. And so we spent a bit of time trying to figure out the best way to sort of fill in the blank here. What we ended up going with for transition systems is we provided a Lean encoded catalog of about 30 temporal logic formula patterns that are commonly used in concurrent and reactive systems. So this is based on a paper from 1999. These guys have a website about this project. It's really interesting if anyone's interested in temporal logic properties. But basically you just have, this range of different sort of property patterns that encompass a wide array of possible use cases in temporal logic for finite state verification. And so we thought, supporting this sort of scheme would be enough to significantly facilitate the strategy specification process. So through our user interface and our Minta tool, we can allow the specification of LTS properties without writing Lean code manually. So this is sort of the input, right, to our Lean Minta workflow. This is just a data structure representing a decomposition strategy. So you have the parent claim here, and then the properties you're using to decompose the parent claim. But really what's happening here is that in gray here, these are the particular formula patterns from our catalog that the user has chosen, right? So proceeds globally, absent before, proceeds globally. And then in red here, these are just either states or actions from the particular system model that they provided. So just by choosing from a drop-down menu which formulas they want and which states or actions they want to include in those formulas, we can have them actually put it into the rest of this sort of templated code without having to learn how to write Lean themselves. Okay, so now that we have a method to specify a decomposition strategy, we wanted to use Lean's metaprogramming framework to at least try to find a proof that is deductive. So basically what we're hoping to do is to take the input, which is a Lean expression of a decomposition strategy, apply some tactics for showing that a decomposition is deductive, and then either Lean will prove that it's deductive and return a tactic script of that proof, or it'll be unable to justify it and then hopefully provide some useful feedback, all right? So since we assume, we might have users who know Lean and users who don't know Lean, most of the automation we've tried to use this for the ones who don't know Lean. So if we assume that the properties are going to be used and are chosen from our catalog for the process that I just showed, then one way to do it, a rather simple way, is just to build a database of proofs using those particular patterns because they're finite in number. and then base our automation or decision procedure around that. So as an example, one of our property patterns is that you have two, either states or actions, P and Q. And this pattern just says, if Q happens, P must happen first. So this is a predicate of paths in an LTS. And there's different ways, of course, that you can show this. So it can hold either because Q never happens, it can hold because Q can't happen before P, or because the precedes relation is transitive. So these are all different lemmas that we've proved about how you might go about showing that in a particular path P precedes Q, right? So our simple decision procedure to finding these proofs is just to use the parser monad to parse the input strategy, which is a text file like I showed earlier. That's a text encoding of a lean object. Basically do some pattern matching on the target. So what is the formula that you're trying to prove? And then just recursively pattern match on the premises and go through the list of known proofs based on that original target. And then either lean will find one that it can use and return the full tactic script, or it'll fail and then it'll just return maybe a partial tactic script that can still be useful in some case. So this is an example of just part of the simple decision procedure that we've based on. At this point, lean has parsed the context and done a little bit of pre-processing, and is just pattern matching on the target for what the goal formula pattern is. So has all these different branches that it might follow depending on what you're trying to prove. And then once you've got a particular, so this is like within a particular target that you're trying to prove, it has some data based on the targets that it's trying to match up with. Has a string that's the current state of the tactic script that it's incrementally building. And it'll just recursively try different lemmas that it knows about this particular target until it can either find something that works or it goes through all the possibilities and then fails. And so this is, if we do find something that works, it'll apply that tactic to close the goal state. And then it'll format everything into a nice string that can be just plugged into the tactic script, which is the output for the user. So for example, if we're a Minta user, we want to verify a claim decomposition regarding a vending machine system like we have here. The first thing we do is create a system model in Minta, which basically just looks like this. It's just a bunch of nodes. It's a directed graph, basically. Then we can perform a model to lean translation within our system. So this is a screenshot of the Minta view for an engineer. So they have the Minta model object of the vending machine. They have this to-lean process, which automatically takes that and turns it into the definition of that LTS in lean, and also a main file that is basically the file that the tool invokes to try and verify decomposition. So next we specify a proper decomposition strategy. This is just a similar example to what I showed before. And then receive a complete or partial tactic script. So in this case, for this particular example, the property you want is that pay precedes restart, and that pay precedes serve and serve precedes restart. And then as you'd expect, lean finds here, which is the part that the decision procedure returns, that it found a transitive lemma to prove that particular property. The rest of it is pretty much just boilerplate around the way that we've formatted our decision procedure. And that's pretty much it. So in terms of what we've been able to contribute, well, first of all, we've done formalizations of assurance cases, transition systems, and temporal logic. Although, as a caveat, the assurance case formalization is very simple, and the transition system and temporal logic formalizations are not necessarily novel at all. But hopefully, it'll still be useful potentially for someone. We've also, we've got this methodology for integrating lean or other proof assistance in this sort of assurance case domain, which we think is useful. And also, we think this is an interesting case study in using lean in a new domain. I don't think anyone has tried to integrate lean as evidence in software assurance cases. So I hope that there can be discussions that happen about this maybe. And in terms of what we've learned, we really believe that lean has potential for contribution in this area, because formal evidence is so much more useful than implicit deductive reasoning. We've learned a lot about, trade-offs in terms of integrating something like Lean with a user-friendly modeling tool. So, how much usability do we want? Do we want our users to be able to write Lean, and if so, how much? Different challenges in integrating Lean with our tool, different trade-offs in how expressive we want the tool to be, what we can do with the automation in Lean. And finally, just for myself personally, it's been extremely rewarding to learn how to use Lean and meta Lean. I mean, I've only been learning Lean for 5 or 6 months and doing meta programming for a fraction of that time, and I'm sure that people in the audience would have a lot of better ideas of how to use it more effectively than I've done here. But I've still really enjoyed it, and the community has been very helpful in sort of helping us along in this project. And then for future work, right now we're just improving the user interface for Minta. Every week I'm finding out new ways to improve the meta programming, so that's an ongoing task. And of course, because we've only been using as our domain these transition systems, we of course want to generalize beyond that to different kinds of models that are used in the software modeling suite. We also need to sort of look more closely at how to use evidence generated by Lean in real-world assurance cases. So at some point in the assurance case writing process, you have to take this sort of informal claim about a system and offer up a representation of that claim in Lean, and then argue, in the real world that we think this formalization is actually accurate both to our informal claim and to the system itself. So that's it's a process that's important, has to be taken seriously. We also, we're still looking for new ways we can find, deductive reasoning or formal fragments of assurance cases, and related to that, how else can we use Lean or similar tools in this this sort of domain of finding formal evidence for assurance cases. And finally, we're going to be looking at, what have we been able to do with Lean 3 and how does Lean 4 change this? So one thing we've been talking about for a while is there some sort of DSL that we can come up with that would make either the usability or integration process easier? I still have to catch up with all the Lean 4 talk that's happening this week, but it all seems very interesting. And so there might be something in Lean 4 that dramatically changes what we've been able to do, but that's still to be determined. And that's it. Thank you so much, everyone, for listening to this talk.
Thank you. Are there any questions?
Yeah, I have one. You mentioned that it's useful in the automotive and the airline industry, and I've had some work with code in the airline industry, so I know to what great extremes they go to verify the code. But lately I've been working with bioinformatics, and if you know CRISPR and microfluidics, and the genetic stuff and all that stuff, this is part of why I'm here. I'm wondering that kind of assurance and the provability of the code needs to be applied to some of the code that they might start using in the world of bioinformatics, because all of a sudden somebody's going to realize, hey, we can start automating the generation of drugs in about 10 years based on taking a sample, DNA sample or something from you. And I'm wondering, has anybody contacted you or talked to you about using this to verify code that might automatically start generating drugs or something? I know it's 10 years down the road and it's a crazy thought, but it's all converging rather quickly.
Yeah, so I haven't heard anything from that particular domain. Again, our focus is mostly on automotive, and so we have, but it was pretty recently we had this new ISO standard that requires this sort of structuring of evidence in this formalized way for that particular industry, and so different industries are choosing different ways that they make these sort of claims. Automotive has this ISO standard, but it's increasingly becoming the case that people are using this more flexible but more structured argument to make high level claims. So I wouldn't be surprised if it might be useful in that domain at least.
Thank you.
Does anyone? Oh, I have a question. So what is the level of complexity of the claims that you can formalize? So I mean, I assume that from your picture, it seems that these formalizations essentially represent single nodes in that graph of you know, you have from one claim to many claims, or I guess the proof goes in the other direction. But that unit is the thing that you can actually verify.
Mhm.
How, I mean, my assumption a priori would have been that the logical form of those things are generally rather simple, like some kind of modus ponens kind of application. What is, yeah, how complicated do they get?
Well, I mean, in the real world, these you know, large structures, like these tree-like structures, are you know, the author is the one who decides what goes where, and so there's a lot of flexibility in what its form looks like. Right now in our formalization, we've just been looking at one target claim decomposed into a list of subclaims. We would like in the future to be able to, you know, take this whole tree structure and then analyze all the dependencies between the claims and the subclaims and what evidence or assumptions or axioms are at play, and have some more interesting, you know, logical analysis of that. But so far, we've just been using the sort of small scale stuff.
Okay, maybe we can pick up a few minutes before the next talk.
Yeah. Yeah. Do we have the next speaker?
Yeah. So, thanks again, Logan.
Thank you.
Pleasure. Thank you, everyone.
Okay.